Okay, so here we are with lesson number 2. We're just going to look at, for the most part, collision theory, and we'll start on this bottom part here. But let's take a look at what exactly collision theory is, and this is one of the definitions that you should know. Basically, the collision theory tells you what needs to happen in order for a chemical reaction to actually occur. Just because you put reactants in a container together does not necessarily mean that they're going to actually react with each other. Sometimes it takes relatively little energy for them to react. Sometimes it takes a lot of input of energy for them to react. But in order for a reaction to occur, you must have what is called an effective collision. And an effective collision involves two things. That means that the reacting particles, the substances that you're reacting, have to have, one, enough energy. That would be probably, I would look at it as kinetic energy. And they have to have the proper alignment, which means that when they collide with each other, they must collide almost head on. So if you have these two conditions, you'll have what we call an effective collision. And most of what we're going to be looking at, especially in the next section, is what can we do to increase the number of collisions, the number of effective collisions. And why is that important? Well, because if the more effective collisions you can force to happen, the faster the reaction is going to occur. And in general, scientists, when they're doing experiment, or even in industry, they want the reaction to occur as quickly as possible, because, as you know, time is money. So if you can do something to a reaction to make it occur quicker, to make it occur faster, that would be to your advantage many times. So what we're going to be looking at in the next couple of sections is what can we do to increase the number of collisions, because when you increase the number of collisions, you're going to increase the number of effective collisions, meaning you will speed up the reaction. Very rarely in science and in industry do we actually want to slow a reaction down. Most of the time we want to speed that up, and that's what we are going to be looking at. And I think probably the best sort of analogy to look at collisions and how you can increase them and decrease them is, and I use this in class a lot, is if I use our classroom. If I took all of the tables and chairs out of our room and then I brought in 6 students blindfolded, those students would represent the reactants, the particles that I want to react. And what can I do? And every time they collide with each other, if they're moving fast enough and they collide head on, that would be considered an effective collision. So you can think to yourself in your head, what can I do to those students to make them react faster? How can I make them collide more? And we're going to look at things like temperature, concentration, pressure, etc. Now, not everything that we're going to look at in the next section is going to do that. For example, if you look at the bottom, the nature of the reactants really has nothing to do with that particular section, but we're going to look at it anyway. Well, let's look at the bottom one here. There are 6 things, there are 6 factors that can affect the rate of reaction, that can either slow it down or speed it up. The first one, which is probably the most difficult to explain and then, of course, to understand, is the nature of the reactants. Now, what does that mean? Well, this has to do with the type of bonding, for the most part, that your substances have. The 2 main types of bonds that we talked about were ionic bonds and covalent bonds. Covalent bonds are stronger than ionic bonds. So in general, if you have reactants that are covalent or molecular, those reactions are generally going to be slower than reactions that contain ionic reactants. Just because covalent bonds are stronger, it takes more energy for them to react, so those are generally going to be slower reactions. And it gives you a couple down here. Ionic is less bonds to break, so there's less steps. Generally, covalent molecules are larger, which means there are more bonds to break. There are going to be more steps. It's going to be a slower reaction. So in general, ionic substances react faster than covalent substances. One of the other things that is important in this is that if you remember when we talked about this in the previous unit, Unit 7, if you remember what happens when you put ionic substances in water, half the job is already done, because when you put sodium chloride, for example, in water, and let me just draw this. Oops. If you remember what happens, I'm not really sure what happened here. Okay. If you remember what happened, let's see if I can do this now. Oh, no, not good. There we go. What happens is when you put sodium chloride, for example, in water, we already know what happens to it. The water molecules break the Na and the Cl apart. So you have Na plus ions floating around and Cl minus ions floating around. So really half the job is already done. When you put this in water, it already splits apart into its ions. So you've, in a sense, already broken the bonds between them before the reactions even occurred, whereas when you put, for example, sugars in water, that doesn't happen. The carbons, hydrogens, and oxygens stay intact, so you now need to break those covalent bonds, which, of course, are extremely strong. So that's the collision theory and the first factor that affects reaction rate.